Okay. So let us move forward. So let us move forward and do a few more things, and let us find how to go about them. Okay. So what I was doing in the last class was about something called as all these things. Like I was talking about in the last class, what I was talking about uh, Cauchy's integral theorem and some consequences that may arise from the Cauchy's integral theorem. One of the uh, similar things that we find in mechanics also, or in general in conservative vector fields also, that if I am dealing with a line integral of a conservative vector field, so let's say if I'm talking about a line integral of a conservative vector field, it may be anything. Let's say if it's a Newtonian kind of force deriving the potential is like a central potential. Okay, for all those kind of things where you have a conservative vector field, the line integral of that conservative vector field along the points r1 to r2 would eventually depend only on the initial and the final points and would not depend on the path taken. A similar such statement you'll find in the Cauchy's integral theorem also. So you see there is a symmetry. So here you can see that if I want to integrate over this entire closed curve C, it amounts me to saying that this is integral would be equal to integral over C1 plus integral over C2. And eventually you'll find that this C1 integral would be equal to minus C2. Understand what is C1. So you can see that I can transform my C1 to this particular line, and I can transform my C2 also to this particular line. And eventually I would say that this would be integration from A to B. So I can integrate my function from A to B in whatsoever manner. Like if I go along the line, if I go along C2, or if I go along C1, like in this direction, they mean one and the same thing. Okay, so this gives me a very powerful statement in complex analysis, or something which has a uh, this is something that you've already done also, that if your function fz is analytic, and if you try to integrate in region R, and if you try to find a line integral along the from points z1 to z2, where z1 and z2 are contained in the region R, then this particular line integral would be path independent. Okay, it would be path independent. Okay, shall I move ahead now? Let us do some sort of exercise, and let us find there are a few more things, like there are a few more trivial things also that I would do in certain different lectures also. But today I want to draw your attention to some important integrals that we did yesterday. Okay. Uh, so what did we do? Yesterday we were doing an integral dz upon z. Okay. So yesterday I was doing an integral dz upon z. And let's say I'm saying my c is mod z equal to 1. Let's say my mod z is equal to 1. That is, I'm talking of a unit circle. So if I'm talking of a unit circle, what would be this integration? What would be this integration? This is what my question is. So try to find an integration of this and give me an answer. Iska answer kya hoga? What will be an answer to this? I want to actually, I don't have any time to, what I can say, I don't have time to derive the entire thing, but I want to take you to the calculus of residues. So I just want certain motivation, and that keeps alive. Okay. Okay. So clearly you can see that this encloses the singularity. So now, for that matter, I would say this encloses the singularity. Okay. So this encloses the singularity. So if I'm moving like counterclockwise, if I'm moving counterclockwise and I'm saying over this particular curve C, find me this integral. Find me this integral over this curve C, and you would say, okay, there is no difficulty about it. I will simply take e to the power iota theta, and I would integrate it. I would simply integrate it, and I would say that, okay, this integration would amount me to say theta equal to 0 to theta equal to 2 pi. I can write it as e to the power iota theta d, I think d theta, divided by, I think, e to the power iota theta. Okay. And this gets cancelled, and this will give me answer 2 pi iota. You can do this entire thing, the same thing, using slit construction also. So you can do the same thing here also. So basically, you can transform your this thing. You can transform, but you cannot go beyond this. So even if it was not a circle, even if it was a smaller circle, or probably only a very minuscule of a circle with epsilon greater than 0, the answer would have remained the same. The only point is I cannot enclose, I cannot go and deform myself into the origin now, because origin z equal to 0 is a singularity right now. Okay, so if I have to find an integral over this closed curve C, I would choose these parametric coordinates, and I'm conveniently to a position to say that this would amount me this will come out as 2 pi out. Now, what would it be like? I'm just giving you an inspiration. That is why I'm doing it. So let's say if I'm doing dz upon z raised to power n plus 1, and if I'm trying to find what would be an integration to this, just try to find an integration of this. Again, integration over like a unit circle. So if I try and find an integration over a unit circle for this particular function, that is 1 upon z raised to power n plus 1, what would I find? I will write it as theta equal to 0 to like a 2 pi. I think I will write as e की power iota theta d theta. I think divided by it will be equals to e की power iota n plus 1 theta. Okay, and this gets cancelled, and I will be having only e की power minus iota n theta d theta integration from 0 to 2 pi, if I'm not wrong. Okay, and I will get I think e की power minus iota. You just try to integrate it. I think this will be n. I think if I should write in this fashion. Theta, 1 मिनट को. So this is now. So ये इसको एक काम करते हैं +1. अच्छा एक काम करते हैं इसको इंटीग्रेट करने के लिए क्या कर रहा हूँ. I have to integrate e की पावर थीटा ना. So e की पावर थीटा का इंटीग्रेशन क्या होता है? e की पावर थीटा इंटीग्रेशन इज e की पावर थीटा. So this will be it. So integration would be equals to what? Iota upon minus iota n e की पावर minus iota theta. Okay. Yes or no? So this gets cancelled, and integration this will become from 0 to 2 pi. So e की power minus 2 pi iota n is 1, and e की power 0 is 1. So this will get cancelled 0, provided n is not equal to 0. Because at n equal to 0, this will reduce to this particular expression. Are you getting my point? ये चीज समझ में आई भरत को? n equal to 0 पे तो ये वाला केस बन जाएगा जो ऊपर किया था. This is giving me an answer 2 pi iota. And if it's n is not equal to 0, then this is giving me an answer this. Are you getting my point?
सर क्या आंसर मिल रहा है n नॉट इक्वल टू 0 पे?
n नॉट इक्वल टू 0 पे 0. देखो ध्यान से देखो, e की
Zero.
पावर माइनस आयोटा n थीटा, ये हो जाएगा e की पावर माइनस आयोटा n थीटा डिवाइडेड बाय माइनस
Yes,
आयोटा
sir.
n, ये
1
कैंसिल
minus
हो
1.
जाएगा, और ये हो जाएगा e की पावर माइनस 2 पाई आयोटा n. कुछ फर्क नहीं पड़ने वाला. cos 2 पाई n चाहे माइनस में लो चाहे प्लस में लो, तुम्हें हमेशा आंसर 1 ही
Right,
देगा,
sir. Right.
और साइन हमेशा
ठीक
0 ही
है.
होता है. 0 पे हो जाएगा ये 1 minus 1, तो इवेंचुअली यू विल गेट एन आंसर इज 0. So why I'm taking this as an inspiration, because see, I cannot go on and derive things for everything, but you can clearly see that this entire thing, what does it suggest me? It suggests me that if I have a singularity, here it was z equal to 0 precisely, and if I am encircling that singularity with a closed curve C, and I'm trying to find an integral, it is very much possible that integral may come out as 0, may come out as 0 or may not come out as 0. Okay, so in similar words, I would say that let us take this example. Let us take this entire example. Okay, so what this example would suggest me, that if I just normalize it by 1 upon 2 pi iota, that is, instead of having asked integration dz upon z raised to power n plus 1, had I asked you integration dz upon z raised to power n plus 1 over this circle mod z equal to 1, it would have been Kronecker delta n comma 0. I hope you are aware of Kronecker delta. If you're not aware of Kronecker delta, I will write here. So Kronecker delta n comma 0 would mean 1 if n equal to 0 and 0 if n is not equal to 0. Clearly, this particular integral would become this. Yes or no? Is that clear? So eventually, you're finding that if you're encircling a singularity, and if you try to find an integral enclosing a singularity, it is way possible that it may be 0, it may be not 0. Okay. And in order to codify this entire thing, we introduced something called as residue. In order to codify this entire thing, that is, what if you have a singularity? So in order to codify all these things, codify this particular value of the integral, we have introduced something called as residue. And this entire subject where we'll be now we'll be heading to is called as calculus of residues. Okay, and this is a very extremely important topic from here on. This is what we actually use in our mostly we use in physics is something called as calculus of residues. So whatever premise I was discussing to you, whatever thing I was discussing to you was to take you to take you to a very important concept in complex analysis called as calculus of residues. Okay, so understand my point. This, for example, if I'm saying, my function is to be integrated over over a curve C where I have a singularity. Let's say here, if there's a one singularity, this 1/2 pi iota is called as a residue. This entire thing is called as a residue. Now, question arises how to find these residues. The question arises how to find these residues. Okay. A question arises how to find these residues, and here I'm just writing it that what we acknowledge residue as, I'm not going into derivation, what we acknowledge our residues as is nothing but V inverse. So V inverse is the residue of Fz. So for example, if I am expanding my Lorentz series expansion at z about z naught, so clearly Lorentz series expansion was always expanded about a point of singularity. And what does this residue look like? So what is this residue? Residue is nothing but it is b minus 1. Now you will be saying, what is b minus 1? I told you in the Lorentz series expansion that if I am expanding my function at z equal to z naught in the terms of Lorentz series, it gives you a regular part given by an z minus z naught raised to power n, and another part b minus n divided by z minus z naught raised to power n plus 1. Are you getting my point? So the part which corresponds to b minus 1, the part which corresponds to b minus 1 is your is called as your Lorentz series. Is called not Lorentz series, is called as a residue of function fz at z equal to z. Are you getting my point till now? Should I वापस बोलूं इस चीज को वापस?
क्लियर सर,
क्लियर है ना? मतलब मैं और डिफिकल्ट तो कुछ एग्जांपल ना दूंगा, मतलब बेसिकली आई डोंट हैव एनी मतलब डायरेक्ट डेरिवेशन नहीं बता पाऊंगा मैं, तो मैं सीधे तुम्हें एक मतलब तरीके से चीज समझा रहा हूँ कि लेट्स से इफ आई वाज एनसर्कलिंग इन सिंगुलैरिटी and if I were to find this particular integral, I found that this integral may be 0, may not be 0. So eventually I found that this, how to say what is this. So basically I told that this is nothing, but I codify this entire thing in terms of something called as residue. And what is residue? Residue is nothing, but it is the term b minus 1. B minus 1, are you getting my point? The term which was in the expansion of, I think, Lorentz series. So for example, if I just try to say, if I just want to say what will be the, just give me an answer, quick answer to this. What would be the residue for function e raised to power z upon z minus 1 ka whole square? So clearly you can see that z equal to 1 is nothing but it is a double pole. So it is a double pole. Okay. पहली चीज तो दिख रही है, fairly easy to see. And what will be the Lorentz series expansion? So if I expand about z equal to 1, so clearly z equal to 1 is a singularity. If I want to expand about z equal to 1, what I would do, I would write z minus 1 as u. So you'll get e raised to power u plus 1 divided by u square. Yes or no? And eventually you can do this, all sort of things that we did in the earlier classes. Okay. And what you can do, you can simply write it as, I think, you can write it as e upon u square plus e upon u plus 1/2 factorial e, and then there will be some principal part, there will be some regular part which I'm not interested in, and you can clearly see that this will be equal to e upon u square, this will be equal to e upon u, and this will be equals to e by 2. Okay, so if I write this principal part term, I can write it as e upon z minus 1 whole square. Okay, then e upon this will be equals to z minus 1, and this will be equals to, I think, e upon 2. Now compare this. So basically an z minus 1 का होल मतलब कुछ टर्म्स होंगे उनको भूल जाओ, प्लस समेशन b minus n divided by, I think it was z minus 1 raised to power n plus 1, if I'm not wrong. This was your principal part, yes or no? Just try to find it. Just try to find, was that your principal part or was that not your principal part? अच्छा b n plus 1 नहीं n है, sorry, my mistake. एक मिनट क्योंकि आप ऑलरेडी, या तो फिर जीरो से स्टार्ट करो, ठीक है, सॉरी. सो बेसिकली क्या रहे हैं, सो बेसिकली इफ आई वांट टू फाइंड b minus 1, so b minus 1 is nothing but it is equal to coefficient of 1 upon z minus, yes or no? यहाँ पर कुछ गलती तो नहीं लिखी ना मैंने? अच्छा ये मैंने इंडेक्सिंग लगाई नहीं थी, बहुत ही
It's
n equal to 0 से चालू होगा. हाँ, yes tell me. So this,
sir,
हाँ बोलो. So coefficient of 1
sir, it will be the independent term, independent of z ना, residue.
हाँ इंडिपेंडेंस है, बस कोफिशिएंट ऑफ 1 अपॉन z माइनस 1. मैंने बोला ना b माइनस 1, तो ये इससे एसोसिएटेड टर्म b माइनस 1 मतलब
सर
अरे
माइनस
भाई
1 प्लस 1 0 हो जाएगा ना, तो 1
एक
इंडिपेंडेंट ऑफ
एक
z
काम
है.
करो, इसको एक काम करो, ऐसे करो, नहीं तो कचरा हो जाएगा तुम्हारा. n इक्वल टू 1 से स्टार्ट करते हैं, ठीक है, माय मिस्टेक. ओके, सो इफ आई वांट टू फाइंड व्हाट विल बी b minus 1, so b minus 1 would be equals to what? b minus 1 would be the coefficient of 1 upon z minus 1. So coefficient of 1 upon z minus 1 is what? 1 upon z minus 1 का कोफिशिएंट क्या बेटा? e. So residue will come out as e. Yes or no?
Yes sir.
Okay, is it clear to you? Actually, I made mistake while writing the Lorentz expansion. Okay, so Lorentz expansion contains, I wrote, it contains a regular part, then it contains a this thing, what I would say. So if I have to say, it is my mistake here. You just write n equals to 1, and you just write raised to power n. Okay, so you have to just find the, in other words, you just have to find the coefficient of 1 upon z, मतलब z minus z not raised to, मतलब b minus 1, समझ पा रहे हो? तो b minus 1 is the coefficient of 1 upon z minus 1 in this scenario. So आप करें, what you have to do, you have to simply find me the coefficient of the what you can say 1 upon some linear power. Okay, so that will give me the answer of the residue. Is that clear to you? कि नहीं क्लियर है? मैं वापस बोलूं?
Yes sir, clear.
ठीक है, फॉर एग्जाम्पल अगर आपका फंक्शन क्या कहते हैं सिंगुलर है ही नहीं, और मान लेते हैं कि इट इज क्या कह सकते हैं, इट इज एनालिटिक, देन द रेसिड्यू विल ऑब्वियसली कम एज 0. Okay, because if your function is not singular, then it will not contain principal part. Sorry, if your function is analytic, then your function will not contain a principal part term. Since it does not contain a principal part term, where will v minus 1 come? Okay, so understand my point, that if I am having uh, analytic function, then the residue will come as 0. Are you getting my point? ये चीज समझ में आ रही कि मैं समझा नहीं पा रहा हूँ? Is that clear to you?
Yes sir.
Okay, let's say if this entire thing, जो इंटीग्रेशन अभी हम सीख रहे हैं, अभी हम सीखने जा रहे हैं, so that is called as, I will write as Cauchy's residue theorem. पहले इसको समझते हैं, what is Cauchy's residue theorem, and फिर हम आगे बढ़ते हैं. So let's say I am to find an integral. I have to find an integral. मैं ऐसे लिख देता हूँ. It states that, so you can write theorem of residues states that क्या कहेंगे, if a function is analytic, if a function is analytic on and inside a positively oriented contour, that is in the anti-clockwise sense, positively oriented contour C, except at some, I think, isolated singularities, except at some isolated singularities, let's say z1, z2, dash, 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 zn of fz, then this integration fz, you can take another like variable inside fz over this uh, positively oriented closed contour is equals to 2 pi iota into summation of residue of function at all these singularities where I varies from 1 silica n. Okay, so this is your theorem which says that if you want to find if you want to find an integration over a closed curve C, you want to find an integration over a closed curve C which contains what? Which contains nothing but it contains, let's say, singularities z1, z2, z3. Okay, then what is an answer? You just find residue about these points, residue function about these points, add them up, multiply it with 2 pi iota, and you will get an answer of what is the value of the integral of function over this closed curve C. Okay, and where does it derive its inspiration from? So I'm just telling you inspiration. I'm not going to derive it. I'm just telling you what was the major motivation and what led to this. So basically, a very simple thing. Let's say this is your closed curve C, and let's say these are your singularities. Since they are singularities, what would one do? One would try to evacuate them. One would not try them. One would not say कि इसको मैं ले लेता हूँ. So what would somebody do? Everybody would try to make a circumference around this, an infinitesimal small circumference. And again, the same thing, slit construction would be done. And while you do these slit construction, what you'll find that integration over on this particular region R, because now after slit, you have removed these things from your region. So basically, you are circumventing these singularities by enclosing them in certain circle and joining them with a slit sort of thing. So now integration over this entire region, this closed integration around this entire region would come as 0. And this will give you that integration over C would be equals to what? Integration over C1 plus integration over C2 and plus integration over C3. And I told you this integration over C1 encloses a singularity. And I told you what is the codification of this particular integration. I told you 1 upon 2 pi iota integration of function encircling a singularity. Encircling a singularity is called as residue. Multiply 2 pi iota here. So this will give you 2 pi iota into the residue of the function at this particular point, 2 pi iota into residue of the function at this particular point, and 2 pi iota into residue function of this particular point is equal to the integral of function. So these were, I think, when I will be encircling, this will be clockwise. So this will be minus clockwise. This will become clockwise, clockwise, clockwise. So eventually, you see the power of slit construction that we did in the multiplicative region. So here it is used in this sense. Are you getting the point? नहीं समझ में आया? कि समझ में आ गया?
यस सर समझ में आ गया।
देखो हुआ क्या, जैसे ही तुम्हारी ये सिंगुलैरिटीज बनी ना, तो बेसिकली अब क्या होगा, ये सिंगुलैरिटी तो आपके उस जोन में तो आ ही नहीं सकती जहां फंक्शन एनालिटिक, तो आप क्या करेंगे, यू विल सिंपली कंस्ट्रक्ट अ स्मॉल सर्कल अराउंड इट. नाउ ट्राई टू मेक अ स्लिट कंस्ट्रक्शन. दिख गया? अब अराउंड अगर ये घूमे इस तरीके से आए एंड देन अगेन यू आर गोइंग दिस वे, देन अगेन यू आर गोइंग दिस वे, अगेन यू आर गोइंग दिस वे, सो along this particular entire thing that I'm right now encircling, my integral would come out as 0. This is a closed region. And along this entire closed region, your function is analytic because now you have circumvented these singularities by enclosing them to a certain radius of epsilon tending to 0. Okay, so this integral would come out as 0. And eventually, what does this integral comprise? This integral comprise this in clockwise, this will be a clockwise, then along this in anti-clockwise direction, along C in anti-clockwise direction, along C1 in clockwise direction, along C2 in again clockwise direction, again clockwise, and this entire thing equal to 0 would give you this. Eventually, I told you that any integral, when you are encircling about a singularity, if the singularity is enclosed within a, let's say, circle C1, this 1 upon 2 pi iota fz dz is a residue. So 2 pi iota into residue. So this is how you write this particular expression. Are you getting my point? Now question arises as to how you will be able to find the singularity. So how would you be able to find the singularity? So this is the last topic that I'm teaching today. So this is calculation of residues, and we'll take it from here only, from tomorrow onwards. Okay. So first case, if your singularity is a simple pole, if your singularity is a simple pole. So what does simple pole mean? So for example, if my function is singular about z equal to z naught, if my function is singular about z equal to z naught, then how would your Lorentz series expansion look like? The Lorentz series expansion would look like n equal to 0 to infinite, an is z minus z naught raised to power n plus, I think only one term in the principal part, that would be this. Yes or no? Yes or no? फटाफट बताओ. There would be
Yes, sir.
only one term in the principal part, and this would be this. Okay. Now the question arises, how should I extract b minus 1? How should I extract b minus 1? So क्या करो? Simply multiply this entire thing with z minus z naught. तो जैसे तुम z minus z naught से multiply करोगे, so what you will get? You will simply get, when I multiply with z minus z naught fz, and if I take limit z tends to z naught, if I take limit z tends to z naught, what I'm left with? I'm left with b minus 1. Clearly you can see this z minus z naught if multiplied with fz would give me an z minus z naught raised to power n plus 1, and here you are left with only b minus 1, because z minus z naught when multiplied with this gets cancelled, so you simply get b minus 1. Here you are getting z minus z naught raised to power n plus 1, and when you take limit z tends to z naught, this entire thing would become 0, and you are only left with b minus 1, in which you are interested. So b minus 1, which is the residue, is nothing but limit z tends to z naught fz. Okay. So this is the value of the residue. If you are having a simple pole at z equal to z naught, you don't have to go through entire derivation. You just remember this formula. So in order to find the residue about a simple pole, the formula is just multiply z minus z naught with fz, take a limiting value z tends to z naught, you will arrive at the residue. Okay. Similarly, if you have a multiple poles, so in that you will have to, should I derive it or should I simply write it? Or should I give it some sort of motivation? So if you have a multiple pole of order m at z equal to z naught, so now what you will have, multiple pole of order m about z equal to z naught. So अब क्या होगा? Now there will be fz would be equals to what? Summation. This will be equal to some z minus z naught raised to power n, and there will be how many terms? There will be b minus 1 z minus z naught. There will be b minus 2 z minus z naught ka whole square, and you will have last term b minus 1 divided by z minus z naught raised to power m. Are you getting my point? Now, in order to extract this b minus 1, what one does is, see, if I want to get rid of all these things, like ये जो नीचे दिख रहे इन सब से तो बचना ही पड़ेगा ना, because if I don't अगर ये नहीं हुआ तो काम बिगड़ जाएगा ना. अगर ये रह गया, let's say if I multiply by z minus z naught, जैसे मैंने पहले किया, as I did in the earlier derivation, if I simply multiply z minus z naught, no doubt I would single out my b minus 1. But then what about these? The z minus z naught remains there. Z minus z naught in the denominator remains. If I take a limit, this will give me an infinite limit. So what one does is simply multiply it by z minus z naught raised to power m. Your function fz is multiplied with this. And you can clearly see that when you multiply this entire thing by z minus z naught raised to power m, this entire thing will become an into z minus z naught raised to power n plus m. This will become z minus z naught raised to power m minus 1. This will become z minus z naught raised to power m minus 2 into b minus 2. This will become b minus m. Now, how to get rid of all these things? Just differentiate it m minus 1. And simply, you will get what? You will simply get b minus 1. But while you are differentiating m minus 1 time, you will get in multiplication m minus 1 factorial. So you just divide it by 1 upon m minus 1 factorial. So this is your b minus 1. So this is your b minus 1. So what you have to do in order to extract b minus 1, you simply have to do this sort of integration. 1 upon m minus 1 factorial into m minus 1 derivative but of z minus z naught raised to power m into fc. This will give you the residue of fz at z equal to z naught, where z naught is a pole of order m. Pole of order m. Is that clear? So for example, if I give you if I say what would be the residue of fz is equal to 1 upon z square minus 1 ka whole square at z equal to plus minus 1. So what would be the residue of fz, which is given by 1 upon z square minus 1 ka whole square at z equal to plus minus 1? Are you getting my point? ये चीज समझ में आ रही है कि it is going way above your head? So देखो यहाँ पर क्या है? It is z minus 1 का whole square into z plus 1 का whole square. Clearly you can see that z equal to plus minus 1 are double poles. These are nothing but double poles. So what you would do is simply multiply. Let's say if I have to find at z equal to 1, you will multiply the function with z equals to 1 ना, तो अपन मल्टीप्लाई किसे कर देंगे? z minus 1 के होल स्क्वायर से फंक्शन को मल्टीप्लाई कर देते हैं. And I will take limit z minus z tends to 1, and since this is a pole of order 2, so I will differentiate with this and this entire thing at z equal to 1, or you can say limit value at z tends to 1. So what you'll get, you'll simply get this as limit z tends to 1 d by dz of 1 upon z plus 1 ka whole square. So what you would get, you'll get limit z tends to 1 d by dz is minus 2 upon z plus 1 ka whole cube. Okay, and I think the limit would come out as minus 2 upon 8, and this will be minus 1 upon 4. Are you getting my point? So at z equal to 1, I think the residue will be equals to minus 1 by 4. Yes or no? And similarly, you can find what would be the residue at z equal to minus 1. Yes or no? समझ में आया? ऊपर से चला गया है?
Sir,
हाँ बेटा बोलो.
sir, if somehow I am able to simplify my function fz into such a way that I am able to write the Lorentz series of it.
Life is easy.
So, sir,
No issues. No issues.
so the
You
1 by z will give me the b minus 1
right,
term, no
right,
residue.
right. So basically वो residue हो गया. For example, मान लेते हैं essential singularity आती है. So let's say if you have an essential singularity, so you are not left with any other thing except what you are saying. So if you encounter an essential singularity, let's say e की power 1 by z. Now at z equal to 0, there is an essential singularity. How to extract the residue here? Just write what? Just try to write a 1 upon 2 factorial, 1 upon 3 factorial z cube. Just write a Lorentz series expansion, and you can clearly see the coefficient of 1 upon z is 1. So residue will be equals to what? 1. Okay. So eventually तुम कर क्या रहे हो? Eventually तुम यही कर रहे हो. थोड़ा ध्यान से देखोगे ना, तो ये मैंने यही किया है. इस पूरी, अगर मेरे को z minus z naught, z equal to z naught पे पोल ऑफ ऑर्डर m मिल रहा है, तो यही तो हुआ लोरेंट्ज सीरीज. तो आपको b minus 1 को एक्सट्रैक्ट तो करना ही पड़ेगा ना. अब b minus 1 को एक्सट्रैक्ट करने का तरीका क्या है? सिंपली मल्टीप्लाई करो z minus z naught रेज़ टू पावर m से. तो देखो ये पार्ट हो जाएगा b minus m, इससे पहला वाला पार्ट हो जाएगा z minus z naught b minus m minus 1. और ऐसे करते कराते तुम्हें इन सबको तो हटाना ही हटाना है. तो व्हाट you'll do, you'll differentiate it m minus 1 times. And because when you are differentiating it with m minus 1 times, so for example, if I say differentiate x cube 3 times, so you will get 3 into 2 into 1. So you'll get some 3 factorial. So therefore, I have divided by 1 upon m minus 1. So this is how you do in for multiple poles. This is how you find residues for simple poles and for essential singularity. Yes, and there is another formula which I'm not going to derive. Just write the result here, and that result is, so for example, if you have a function which can be expressed as quotient of two analytic functions. So for example, if your fz can be written as quotient of two analytic function gz and hz. Okay, gz and hz, and there is a simple derivation to it. You can simply find it in your books also. If this is the case and z equal to z naught, if z is equal to z naught, is क्या कह सकते हैं, is a singularity, is a singularity, or you can say is a singularity of, or you can say is a simple pole, is a simple pole. Okay, so what you can do, you can simply find this kind of formula. याद करो ये करा था, z tends to z naught, z fz into z minus z naught, यही था. अगर z equal to z naught is a singularity और precisely अगर वो simple pole है, तो आप क्या करेंगे? You will simply do this limit z tends to z naught fz into z minus z naught. ओके, अब दो कंडीशन समझते हैं. इफ एट ऑल ऐसा गिवन है, इफ एट ऑल, ओके, इफ एट ऑल ऐसा गिवन है कि z नॉट आपकी सिंगुलैरिटी है, किसकी? fz की, तो पक्की बात है hz नॉट तो जीरो ही रहा होगा. ये सुनो, hz नॉट अगर जीरो नहीं होगा तो काम कैसे बनेगा? मतलब सिंगुलैरिटी का मतलब क्या है? यहाँ पे फंक्शन नॉट डिफाइन होना चाहिए. तो इट इम्प्लाइज दैट hz मस्ट हैव अ zero at z equal to z naught. Yes or no? And what you can do, you can simply Taylor series expand about z equal to z naught, and you will get z minus z naught h dash z, and then you will give higher order terms which I'm not interested in, and eventually you'll find, because hz naught would be zero. So, and given that gz naught is non-zero, इस तरीके से कंडीशन दे रखी है कि gz naught non-zero है और hz naught zero हो जाता है, and because of which fz becomes analytic at z naught. How to find the residue in this particular case? So how would you find? Simply मैंने बताया z tends to z naught करो, z minus z naught से fz को multiply करोगे, तो eventually you'll find that if there is a simple pole at z equal to z naught, and your function fz can be represented by gz upon hz, then the residue is nothing but limit z tends to z naught gz upon h dash z. This is a formula. So for example, if you want to find residue of function fz about point z equal to z naught, where z naught is a simple pole, तो तुम क्या करोगे? I have already stated कि अगर z naught इसकी singularity है fz की, तो आप क्या करोगे? Basically it means that hz naught zero रहा होगा, and given that gz naught zero नहीं है, तो आप क्या करेंगे? Simply try to expand hz in Taylor series. जब टेलर सीरीज एक्सपैंड करोगे तो ये जो डिनोमिनेटर वाला टर्म दिख रहा है ना बेटा, दिस विल बिकम z माइनस z नॉट h डैश, आई थिंक z नॉट, और फिर इस तरीके से कुछ टर्म्स आते जाएंगे. अगर तुम z माइनस z नॉट से मल्टीप्लाई करोगे, दिस विल गेट कैंसल्ड, बट हायर ऑर्डर टर्म्स में मल्टीप्लीकेशन रहेगा z माइनस z नॉट का, और तुम अगर लिमिट लोगे तो इवेंचुअली यू विल गेट अप दिस पर्टिकुलर एक्सप्रेशन. You'll get this expression. So I'm not interested in finding the derivation. I've just given you motivation. अगर fz तुम्हारा इस तरीके से एक्सप्रेस्ड है, दैट इज gz अपॉन hz के फॉर्म में एक्सप्रेस हो सकता है. फॉर एग्जांपल 10z. सो 10z का मैं पूछता हूं तुमसे कि व्हाट विल बी द रेसिड्यू. सिंपली क्या है ये? sin z अपॉन cos z. तो मैंने क्या फॉर्मूला बताया कि z इक्वल्स टू, लेट्स से जो भी इसकी सिंगुलैरिटी अभी नहीं निकाल रहा, मान लेते हैं z इक्वल टू z नॉट पे इसकी सिंगुलैरिटीज हैं, तो व्हाट वुड बी द रेसिड्यू? सिंपली क्या करो इसको, एंड क्लियरली यू नो दैट 10z जहां सिंगुलर होता है, दैट इज पाई बाय 2 3 पाई बाय 2, वहां sin z सिंगुलर नहीं होता है, तो ये तो एज इट इज रहने दो, इसको डिफरेंशिएट कर दो sin z अपॉन माइनस sin z. आर यू गेटिंग माय पॉइंट? तो ये चीज समझने की कोशिश करो कि if at all your function can be represented as some quotient of two analytic function, and if your fz encounters a simple pole at z equal to z naught, the formula for deriving the residue at z equal to z naught will be this. Are you getting my point? ठीक है?
This is only true for simple pole only, no?
This will be true for only simple. We may extend it to different definitions, but usually that does not come in examination. I will do it tomorrow, I think. if at all it like certain things of that sort come. But the condition is that G